I'll break it into two shapes, calling shape 1 the entire rectangle and shape 2 the cutout part. Stick with their given coordinate system, putting it in the middle and bottom of the shape. So the x-axis is down here. By symmetry, we do know the centroid will lie on the y-axis. We'll still go through those steps though. But the x-prime axis will be somewhere above the x-axis. And just like in the last one, it's going to be a distance of y bar above that x-axis. In this problem, I'm asked to find both Ixx and Iyy. Therefore, I'm going to need to know the x tildes and the y tildes, because in the subsequent steps, I'm going to need the dx's and the dy's. Shape 1, the outer rectangle, is 6.5 inches by 14 inches. These are all going to be in inches for this problem. So inches. 6.5 times 14, I'm going to get a positive 91 square inches. Shape 2 is 13 by 6, and it's being cut out, so that's a negative 78. So the total cross-sectional area is only 13 square inches for this channel-shaped beam. Both of them are symmetric around the y-axis, so if I look at the center of my outer shape, it's located on the y-axis, and of my inner shape, also located on the y-axis. Therefore, the x tildes for both shapes are 0. However, the y tildes are not. For my outer shape, its centroid is located up here on the y-axis. So to go from there to the x-axis, that's what y tilde is defined as. So that's going to be half of its height, or half of 6.5, which is 3.25. For shape number 2, its bottom is also on the x-axis, so half of its height of 3 will be its y tilde. Now I just have to multiply. Ax tildes are 0 in both cases. Ay tilde will be 91 times 3.25 is 296. Negative 78 times positive 3 is a negative 234. And adding the total ay tildes, ay tildes is 62. X bar then is 0 over 13, or 0, which we expected from symmetry. And my y bar is the 62 over 13, or 4.75 inches. Now we move on to, we want both Ixx and Iyy. For each shape, we're going to find its moment about its horizontal centroidal axis and its vertical centroidal axis. That's the Ixx prime, Iyy prime. We then also need to find this dx value, this dy value, and then the full adjustment for the parallel axis, adx squared and ady squared. We have to always be careful, are we talking about the horizontal bending or the vertical bending in this case, or which axis we're bending about. So when I'm talking about Ixx, that is its resistance to bending around the horizontal axis that passes through the shape's centroid. And again, this will tell us which dimension is being cubed, or if it's a rectangle or a triangle, and which is linear. For shape number 1, its Ixx, we're going to cube this dimension, the 6.5. So 6.5 cubed times the 14 divided by 12 will be the Ixx for shape number 1. That is going to give us 320. Right, it's how it resists bending about the vertical axis. So now this dimension is perpendicular to the vertical axis, and the 6.5 is the parallel dimension. So it'll be 14 cubed times 6.5 over 12, in which case that will be a larger value, 1486. Going to shape 2, the same idea about its horizontal axis. It will be 6 cubed times 13 over 12, which will be 234. This is a cutout shape, so this is negative. And for its Iyy prime value, it's the 13 cubed times 6 over 12, also a negative value of 1099. I can add down here, and I will get 86. Adding down here, I get 388. These are only the moment of inertia about each shape's own centroidal axis. The goal is to find the moment of inertia about the composite shape about its centroidal axis. So I use these adjustment terms here, these dx and dy, which I then feed into 80x squared, 80y squared. This is where you have to, again, keep track of how I'm defining these things. Dx I'm defining as y tilde minus y bar, and dy I'm defining as x tilde minus x bar. So this is the confusing point, I think, of there's y's here, but it's a dx. There's x's here, but it's a dy. Dx, again, this is the distance between the vertical distance between the centroid of, in this case, the first shape, and the centroid of the composite shape. That's why I'm using the y tilde and the y bar. For shape number 1, it'll be 3.25 minus 4.75. So I will get for dx for shape number 1, negative 1.5. And for shape 2, it's y tilde of 3 minus 4.75. So dx is 1.75 for shape number 2. The dy values will be x tilde minus x bar, 0 minus 0, and again 0 minus 0. Just because the shape is symmetric does not mean these are automatically 0, because it depends on how we split up the shape initially. Had we split it up into a rectangle, a horizontal, and 2 vertical rectangles, our centroid would be at the same point, but now these do have a dy value in this case because they're not sharing the same centroidal axis. So it's going to depend on not only is it symmetric, but how did you divvy the shape out. So I do want to include this step, even though it's going to turn out that when I multiply, these are going to be 0. That's not necessarily the case. And lastly, a dx squared, I'm going to get 91 times quantity negative 1.5 squared. Gives me a positive value since that's being squared. I get 205 for shape number 1. Shape 2, I have a negative 78 times a quantity negative 1.75 squared, results in a negative value, 239. Again, it doesn't really matter if you report these as positive or negative, because they're being squared in the way that we're using them next. You'll still get the same values in these columns. Finally, we can find the total inertia of the shape about its own x-axis, or centroidal x-axis, is 86 plus the 80x squared terms, negative 34. So that total inertia is, with proper rounding here, 52.3 inches to the 4th power. For IYY, we get this total of 388 plus this total of 0, and we get 388 inches to the 4th power.